Hello, welcome to the continuing videos in the linear algebra series. So in this video we're going to talk about another special type of matrix that's related to some of this determinant stuff. Specifically a matrix called an adjoint. And we're going to see how this matrix can do two things. Number one, on its own it can relate to kind of the 2x2 inverse formula. This is going to give a kind of equivalent for higher ones, although we will see it's a much more complicated kind of process. But the theory behind it will also lead us to an alternative way of solving systems of equations, or at least some systems of equations. So before we get started, let's take a look at what we have right here. And so I have two matrices. Granted, I haven't written every single matrix. There's more entries down here and over here. I'm going to take a look at these two matrices right here. And remind ourselves, because it's been touched upon in previous videos, kind of this computation. So right here, this first computation, so the C's are the cofactors, just like in cofactor expansions. So what's that first line equal to? Alright, so that first line is equal to the determinant. And in fact, if we replaced it, did along the second row, we could replace all these 1s with 2s, and we'd get the same thing. Another question that we would have been briefly touched upon in some of the properties is what if we took the same A's but multiplied them by the different cofactors? So instead of the cofactors of row of the first row, we multiply them by the cofactors of the second row. So what we saw in a previous video, although you can verify it for yourself, the theory behind that one is the fact that you're effectively just swapping two rows and you get the exact same answer. Instead of putting the A's on the first row, we put the A's on the second row as well. But swapping those two rows keep the answer the same. But we also know swapping two rows makes the answer negative, so the only way that that's possible is if this is equal to 0. And there is nothing special about the second one. It would also be true if we did the third one, the fourth one, or in general, any I, that should have been a 1 here, any I that wasn't equal to 1. Again, not saying that that's an obvious statement, but it is something that's true and something that we would have seen before in a previous video and probably explored a bit in class. So the point of this is, what does this mean? So what does this actually give us? Well, if the entries match the cofactors, then we get the determinant. If the entries match the cofactors of a different row or column, we always get 0. So we're going to use this in a way of multiplying these matrices together. Specifically, if we fill out the matrix, with all of their entries, what happens if we multiply these together? Well, if we multiply it together, along the diagonal, we would get the determinant of A everywhere along this diagonal. And what would we get off that diagonal? Well, off the diagonal, we would get zeros absolutely everywhere. In other words, we get the determinant of A multiplied by the identity. So this matrix right here, so the first matrix was just A itself. So here's A. And over here, we're getting something that looks a little bit like a cofactor matrix. If we look here, we're getting the cofactors every single entry. However, we'll notice that instead of going along a row, instead, this cofactor matrix, we're going along a column. And so rows become columns where they're supposed to be. In other words, we're dealing with a transpose. Definition, the cofactor matrix C is the matrix whose ith row, jth column entry is the Cij cofactor of A. So that's the cofactor matrix, which honestly on its own does next to nothing for us. The one that's important to us is called the adjoint. The adjoint of A, or ADJA, is the transpose of this matrix. And the whole purpose of this adjoint, at least for us, is this property that A times the adjoint of A is equal to the determinant of A times I. And if the determinant is non-zero, that says A inverse, well, that would be A times something, so we need to divide by the determinant. And we get something similar. Granted, it's much more complicated in terms of actual computation, but we get something similar to the 2x2 matrix that would say that A inverse is 1 over AD minus BC, which is our determinant, times D negative B negative CA. So this would be the adjoint of a 2x2 matrix. However, for 3x3s, 4x4s, that matrix gets more complicated, but we do get a similar property to what we had before. That being said, it's not as quick a computation as it would have been for a 2x2, so whether or not it's useful for a whole bunch of computations depends on some special cases of the situation, but at least it gives us an alternative method, and also something that's going to be useful in another place as well, and we're going to see that in just a minute. So again, in class, we'll probably do a bunch of examples of finding this adjoint matrix. You find your cofactors, you find their transpose, and you go with it from there. For example, the adjoint of 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not an invertible matrix, so we're just computing the adjoint, not the inverse from it. That would be the matrix. So we can start with the cofactor. So that's going to be 2, eliminate row 1, column 1, 5, 6, 8, 9. Eliminate row 1, column 2, but it's negative because it's our place in the cofactors. 4, 5, 7, 8. And you would just keep going. 2, 3, and you get all these little mini determinants. Row 3, column 1, 2, 3, 5, 6. Row 3, column 2, 1, 3, 4, 6. 1, 2, 4, 5. So in other words, you get negative 3, 36 minus 49, 6, 2 minus 3, 6. And this one gets a little weird. 9 minus 21 is negative 18. Six. And forgive me as I'm doing this a little bit fast. But we get this right here. That's that transposed. Now this just happened to be a symmetric matrix. In general, that's unlikely. And there we go. So this is our adjoint and how we can compute it. So it does, on the face of it, does seem like it's a more involved process, because if you wanted to use it to find the inverse, you'd have to then find the determinant and then divide this by the determinant, although full disclosure, this determinant is 0, so it's not even invertible. But one of the nice things that this gives us, which is what we're going to, one thing we're going to use it for, is that it can find specific entries in the inverse without having to find all of them. So our other method for finding inverse, our row reduction method, you find all of them together. And if you're dealing with numbers, not a big deal. 3 by 3s, 4 by 4s, it's really not that bad. If you're dealing with functions or other things inside, it can get really nasty trying to work with them all at the same time. The nice thing about the adjoint method is that we can solve for specific entries in the inverse without having to find all of them. So if you found the determinant, every entry in the every cofactor gives you an entry in the inverse. So if you only needed to find 1 or 2 entries in the inverse, then you wouldn't need to find them all. And that can give us some benefit. So there's some reasons why this, even if it seems like more work to find the entire inverse, there are some uses for this, because sometimes we don't want to find the entire inverse. You know, vague ideas coming from a video. All right, so that's how we can find the adjoint. So there's one more topic I want to mention in what we're doing here, and that's something called Cramer's rule. So Cramer's rule is going to use some of these ideas, right, that we just mentioned. And namely is, okay, if we have a new way of finding the inverse, assuming the inverse exists, then we might have a new way of solving a system of equations. So again, if AX equals B is a system where the determinant of A is not equal to 0. So if the determinant is 0, then this isn't going to do anything for us. We wouldn't do anything, and it'll be obvious why as we go through it. So let's think back to our list of equivalent statements in regards to solving a system. So 2 things on our list of equivalent statements to the determinant of A being 0. The first thing is that the matrix is invertible. So we know here that the matrix is invertible, the A inverse exists. The second thing is that this system has exactly one solution. The question might become is there a way of using the adjoint and the determinant and that kind of stuff to actually find that solution? And that's what we're going to be seeing here. So the idea is, we know there's exactly one solution, and we also know that that solution is A inverse times B, which we now also know is 1 over the determinant of A, which is the adjoint of A, multiplied by B. On the left, order matters. So what is that going to equal? So let's just take a look and see exactly how we found the adjoint, that's C11, C12, down to C1n, C21, C22, down to C2n, and so on. CNN. And we'll slap some B's here as well. So we'll get 1 over the determinant of A. And the first entry, we would take the first row times the only column. So that's B1, C11, B2 plus B2, C21, plus all the way to Bn, Cn1. And some similar stuff down the line. In other words, x1 is equal to 1 over the determinant times that ugly monstrosity that we just computed right there. And we could find the other ones. For x2, replace the first ones, or the ones with 2's, and so on. So let's just take a look. Right here. All right. So, perhaps an interesting question would be, is this the determinant of something? It kind of looks like the determinant of something. But is that the determinant of something? Now let's look at the cofactors. The cofactors going down here, that's the cofactors of the first column of A. So this is going to be our first column of A. However, the B's are not the first column of A, but the cofactors are. The cofactors are the cofactors we would get from the first column of A. So this almost looks like what the determinant would be if we expanded along the first column. The problem is, instead of multiplying by the appropriate values in A, we're going to be multiplying by some random entries in B. In other words, this is going to be equal to the determinant of A, I'll call it A1, over the determinant of A, where A1 replaces, well, where A1 is A, where column 1 is replaced with B. And similar for x2, x3, and so on. And this is Cramer's rule. So Cramer's rule would say you have to find the determinant of A. If the determinant of A is 0, then clearly this doesn't work. But if the determinant of A is 0, then we know the inverse doesn't exist, and we know that this system does not have a unique solution, in which case it has either none or infinitely many solutions, and so we can go back to the row reduction method. We have other methods to deal with those. But if the determinant of A is non-zero, then we can find x by finding the determinant of another matrix and dividing it by the determinant of A. And the nice thing about this is we can solve for x1 or x or whatever the first variable is without having to ever solve for the other one. Now that may not seem like it's particularly exciting if you have to solve the entire system, but there's certainly some practical applications where you only want to solve for one of the variables, and this can solve for one of them without having to ever touch the other variables. Anyway, to see this in action, let's just take a look at one quick little example. So we can solve x plus 2y equals 5, x plus 5y equals 18. Obviously not one that you would need to do anything fancy to solve, but just to get used to the ideas. So if we wanted to use Cramer's rule here, we're first of all going to have to figure out what the coefficient matrix A is. So that's 1, 2, 1, 5. And the determinant of A is 5 minus 2, so that's 3. The first thing to note is the determinant of A is not equal to 0, and hence we can use Cramer's rule. So x1, or in this case just x, the first variable, is going to be equal to the determinant of A1 over the determinant of A. And y is going to be equal to the determinant of A2 over the determinant of A. And once again, one of the nice benefits of this, and there's some other benefits as well, and we'll talk about some of those interesting properties, is that we can solve for x without even needing to look at y, and vice versa. We can solve for y without ever needing to look at x. So A1, so what we were saying is we're going to take A, so we start with A itself. And to determine the matrix A1, not the determinant yet, but the matrix itself, we're going to take the first column of A, and we're going to replace it with the matrix B on the right-hand side. So column 1 goes, and it's replaced with B. For A2, we'll do the same thing. We'll start off with the matrix A, and we'll remove column 2, or the column for y in the original matrix, and we're going to replace that again with the matrix B. So the determinant of A1 is equal to 25 minus 36, so negative 11. The determinant of A2 is 18 minus 5, which is 13, which tells us that x is equal to negative 11 over 3, and y is equal to 13 over 3. And so this gives us an alternative method. One of the pros and cons of every method you might want to think about. One of the nice pros of this method, as mentioned, is we can solve for x without needing to touch y, and vice versa. And that in itself might not seem like it means much if we were dealing with a system like we just had, where we're dealing with some fairly nice numbers. But if the numbers get crazier, then we know that row reduction, if you're dealing with some weirder numbers, for those of you who have seen complex numbers can make row reduction really annoying to deal with, even if it still works. Everything involved in this process involves a determinant, which is just straight up multiplication. You don't have to deal with a bunch of these row operations. Not that that's necessarily a complicated thing, but imagine solving a system like this. And this is very common in something beyond. Would be if you had sine x A plus cos x B equals tan x, and negative cos x A plus sine x B is equal to 0. I'm not saying you're going to do anything like this in class. This is just where this might go. Imagine trying to use row reduction on a system like this. That could be something insanely crazy. But Cramer's rule is a little bit nicer. You would get tan x 0 cos x sine x all over sine x cos x, and everything is multiplication. You wouldn't have to think about All right, well, I'll have to divide through by the sine x in order to get a leading 1. Well, if you divide by sine x, what if you divide it by 0? Well, now you're starting to deal with all these crazy things. You don't have to deal with them in Cramer's rule. That would be sine x tan x. And this would be sine squared plus cos squared, which is just 1. And we can solve for these things without ever having to worry about row operations and stuff like that. Similarly, you could do b. And you would get cos x tan x over 1. And so this allows us a way of doing, when things get more complicated, maybe not just nice numbers, the work here stays the same even if row reduction would get crazier. So that's one of the reasons why Cramer's rule can be useful in some situations, even if some of the things that we might do, it might seem a little overkill. Anyway, that's it for this video, and a bunch of our determinant stuff. See you in the next one.